speaker. He's going to tell us about the motivic atom spectral sequence based on Hermitian K-theory. Thanks, Dominic.
Thank you, Andrew. And thanks Stan and Andrew and the Wayne State team for inviting me to speak here today, and thanks to all of you for showing up. Anyway, yeah. I'll be saying some things about complex motivic KQ resolutions. So here's a brief outline of some of the things I want to talk about today. So because this is a broader audience, I'll probably spend most of my time talking about the history and the motivation behind this problem, and then towards the end, maybe I'll actually talk about some of the technical details. And if there's time, I'll also say some words about future work. So anyway, so let's get started. So let's just talk about history and motivation. So, there are sort of two, so first off, I should say, so everything here is joint work with JD Quigley. Everything I say, I did with him. So anyway, so here's a question that, probably many of us have thought about at one point or another, which is, how do you compute stable homotopy groups of spheres, right? So a very powerful technique was discovered by Adams, I guess in the 50s or 60s. And basically the idea is you take a commutative ring spectrum E, and because it's a ring spectrum, you get a map. You get this map here, that's the unit map from the sphere into E, and you can take the cofiber of that. And so we call that cofiber E bar, and you can twist it around, and so you get this. And so this is a cofiber sequence. So the idea is you keep smashing this cofiber sequence with E bar over and over and over. And if you do that, then you get a tower that looks like this. So this here is the cofiber sequence from the previous slide. And then if I smash that cofiber sequence, so if I smash this cofiber sequence with this cofiber sequence, if I smash this cofiber sequence with E bar, then I get this cofiber sequence. And if I smash with E bar again, I get this cofiber sequence, and so on and so forth. And then of course, remember that, you can extend cofiber sequences so they're like little connecting homomorphisms over here, if you like. So you can apply homotopy to this, so you can apply pi star to this, and you get an exact couple. Right? And so you get an exact couple, and the pi star of the stuff in the bottom row is precisely the E1 term. All right? And then the abutment of the spectral sequence is the homotopy groups of something called the E nilpotent completion of S, which very often does coincide with the Bass field localization, and very often you can describe what that is. But this is the general form of the spectral sequence. Okay, and under favorable circumstances, you get a very nice homological description of the E2 term. So, and that condition, of course, I'm sure a lot of you are familiar with it. It's that E star E is flat as an E star module. Okay, so you need the co-operations to be flat. All right, so there are several examples that you all are probably very familiar with. Probably the most notable example is the case when E is the mod P Eilenberg-MacLane spectrum, in which case you get the usual atom spectral sequence. So this is what atoms actually considered first. And in this case, the abutment is to the homotopy of the P-complete sphere. Another example that people think about a lot is the case when E is complex cobordism, or when E is the Brown-Peterson spectrum, which is a summand of complex cobordism. And in this case, the nilpotent completions are either the sphere or the P local sphere. And in both of these instances, you have this homological description of the E2 term. But these are not the spectral sequences that I really want to talk about today. The spectral sequence that I want to talk about today is more related to a version of the atom spectral sequence which was studied by Mohoald. So Mohoald really, he studied very intensely the spectral sequence that you get when you let E be the connective real K-theory spectrum. Now in this case, there is no nice homological description of the E2 term, but nevertheless, Mohoald was able to do quite a bit of interesting stuff with it. So here's one of the things that he was able to prove using the VO-based atom spectral sequence, sorry, the KO-based atom spectral sequence. So one of the things he did was he proved the height 1 telescope conjecture at the prime 2. So what does that say? Well, so what it says is that suppose you have a finite two-local complex X, and let's say that its rational homology is 0, but that its complex K theory is not 0. Well, under this situation, then you get a endomorphism of X. So you get a map from some suspension of X to itself, such that when you look at its effect in complex K theory, you're actually just getting a map which is multiplication by some power of the Bott element. So this V1 here is just another name for the Bott element in complex K theory. So in particular, that shows things like that if you take if you iterate f(n) times, that's an essential map. That's a map which is not null homotopic. So no composition of f with itself is ever going to be null homotopic because its effect in K theory is non-zero. And so because I have this self map, I can also take this like mapping telescope construction. And so I mean this is just what it literally is. I just take X and then I apply F over and over to X. And I take the colimit over that diagram. This is what V1 inverted X is. Now, if you take this thing, you take this mapping telescope, then it turns out that there's a natural map from this V1 inverted X into the Bassfield localization of X with respect to mod 2 K theory. And the telescope conjecture is asking whether or not this map is an equivalence. If you know, by the way, this is just a side remark. So if you're familiar with this stuff, then Ku mod 2 is just Morava K1. So this is asking some sort of notion. This is asking about about two different notions you might have of V1 periodicity, right? Namely V1 periodicity with regards to composing with a map and V1 periodicity with regards to K1 localization. So it's asking whether or not these two things coincide with each other. And so this is, and Mahol showed that this map here is in fact an equivalence, at least at the prime 2. Okay, so another thing that he did with this, and at least with Wolfgang Wellman, is he showed that you can also compute with this spectral sequence. So he actually, those two actually were able to calculate the E2 term for the KO-based atom spectral sequence, at least in a range, and they saw that in the range T minus S is less than or equal to 20, that the KO-based atom spectral sequence actually collapses at the E2 term. And then this was also sort of we did some work. I did some work with Baudry, Behrens, Bhattacharya, and Shu, and we redid these calculations and extended them, and we saw similar sort of things. Okay, so it's also like a computational device. And then the other thing that he did is he showed that the V1 periodic elements in pi star of this in the stable homotopy groups of the sphere, those are actually detected in the 0 and the 1 line of the KO-based atom spectral sequence. So you can also use it to effectively calculate like the V1 periodic homotopy. So recall that this is what the J homomorphism is. It's a map from the homotopy groups of the infinite orthogonal, the infinite special orthogonal group to the stable homotopy groups of spheres. Okay. All right. So these are some things that Mahowald was able to do with the KO-based atom spectral sequence. So that's sort of one side of the motivation behind this project. But the other side, oh, oops, sorry, yeah, I forgot. This is a picture of the KO-based atom spectral sequence up through dimension 22. So there are some familiar things here. So this is eta here. This is eta squared here. Everyone can see the drawings, right? Okay. And then this is new squared, new cube, etc. So okay. So anyway, so this is a picture of the KO-based atom spectral sequence E2 term. All right. So another side of sort of what motivated me and JD is coming from motivic homotopy theory. So there's this category of motivic spectra called SHK, and you have one for every field K. I don't exactly want to say what a motivic spectrum is or isn't, so I'm just going to kind of tell you a lot of the basic properties of these categories, at least the properties that I need. Okay, so I mean, the main thing though is that, you know, the category of motivic spectra behaves a lot like the category of classical spectra. So namely, I mean, probably the first property you would want it to have is that it's a tensor triangulated category. So it's supposed to have a smash product. With respect to that smash product, it's a symmetric monoidal category. The monoidal unit is the motivic sphere spectrum. You can add and subtract maps from each other and things like that. Okay, another thing is that it's tensored over spaces. What does that mean? Well, that means that if you give me a space, a motivic spectrum X, and a space K, then I can make sense of the expression K smash X, right? So in particular, that means that I can also make sense of the expression S smash X, where S is the one sphere. So what that practically means is that this category has a suspension functor. So there's a way of suspending motivic spectra. And in fact, this category is stable in the sense that if I look at the functor, which takes an X and suspends it, so I smash with S with the topological sphere, then that's actually an automorphism of this category. So what that means in practical terms is that you can make sense of expressions like this. And that's why this thing is also tensored in spectra, because once you invert the sphere, then you also are getting just spectra. Okay. Another thing is that if you give me a pointed smooth variety over K, then you get a suspension spectrum for that thing. So this is exactly analogous to the usual thing in spectra, which is that if you give me a space, then there's a suspension spectrum of that space. So in particular, there are these motivic spectra, which are the suspension spectra of the one-dimensional projective space and the multiplicative group. And the other key feature about this category is that smashing with P1, so at this point I'm sort of identifying these two things with each other. So if you take this one-dimensional projective space and if you smash it, if you take the functor, which is just smashed with one-dimensional projective space, that also turns out to be an automorphism of the stable motivic homotopy category. So you can invert, at least stably, you can invert P1. And that's what this means. Okay, so what the upshot of all of this also means is that there are two kinds of spheres here. There's the topological sphere, which I can smash motivic spectra with the topological sphere, but I can also smash with the multiplicative group. Now, the multiplicative group, if you're saying in the case that K is the complex numbers, then that's just the punctured plane, and that deformation retracts onto a sphere. So it seems reasonable to think of the multiplicative group as some sort of sphere. Okay, but these things are S1 and GM are not like the same motivically. But you have these two different kinds of spheres, and so that means your spheres are going to be bigraded. And so I'm going to use this notation SPQ to denote the P minus Q sphere smashed with Q copies of the multiplicative group. Okay, so here P is like the topological degree and Q is the motivic weight. But anyway, the point of all of this is that you have bigraded spheres, so that means that your functors like homotopy groups or cohomology are all naturally bigraded objects. So everything's in the motivic setting, you know, everything's bigraded basically. Okay, the other thing to mention here is that, you know, there are a lot of motivic analogs of classical spectra. So you have an Eilenberg-MacLane spectrum, which represents motivic cohomology. You have a spectrum called KGL, which represents algebraic K-theory, and that corresponds to complex K-theory. And then you have this other thing, which is going to be really important for our talk, called Hermitian K-theory, which is the motivic analog of real K-theory. Okay, so these things all exist, by the way, over general base fields. At least, I guess, for KQ, you need to make sure that 2 is invertible in the field. Another thing I didn't write down though is also you have an analog of a motivic analog of complex cobordism, which is called algebraic cobordism. But anyway, so at this point, so everything I've set up to now is fairly general, but now I want to specialize to the case when K is actually just the field of complex numbers, okay? So I should probably tell you about some things that are specific to this situation. So I will let H forever and always be mod 2 motivic Eilenberg-MacLane spectrum. So you need to know, in the very least, what the motivic homology of a point is here. And in this setting, a point is just spec of the ground field. So spec of the complex numbers here. And in this case, you get a very nice algebra. So you get this polynomial algebra over the field with two elements on this generator called tau. And this tau is in die degree 0 minus 1. The other thing I should have mentioned was that, I mean, tau is also inside the homotopy of the sphere. But anyway, so this is the motivic homology of a point. You can also think about what the motivic analog of the dual Sternroth algebra would be. And that's given by this formula. And this was first proven by Voevodsky. So the thing to notice here though is that this thing looks like an odd primary version of the dual Sternroth algebra. And in fact, there is a relationship between those things. If I set tau equal to 0, then and if you look at this relationship over here, then I'm setting this part to 0. So I'd just be saying that the tau i's, the generators of tau i's, would be exterior elements. And so then this exactly looks like an odd primary version of the dual Sternroth algebra. And you have similar products. So if you're familiar with the classical dual Sternroth algebra, these co-products should look familiar because they're exactly the same as in the classical setting, but at odd primes. Okay. So another key feature, so there's also another key feature, at least of the complex motivic stable homotopy category, is that there's a very interesting and tight relationship between complex motivic spectra and just regular spectra. And this relationship is through this functor called Bethe realization. So basically the idea is, so a motivic spectrum is built out of smooth varieties over C. Okay, now if you give me a smooth variety over C, you can look at its complex points. So you can just look at the solutions in complex numbers. And because that's a smooth variety, if I look at the complex points, that actually has the structure of like a complex manifold. So it's in particular a nice, it's a nice topological space. And so what you can do is you just can take complex points to take a motivic spectrum and just spit out a regular spectrum. And there's a very nice way of relating the homotopy groups on the motivic side with the homotopy groups on the classical side. And basically, you just set tau equal to 1. So what that means is that if you set tau equal to 1, you're just killing the tau torsion, and you're keeping track of all of the tau torsion-free stuff. And so you can also say, more concisely using this isomorphism here. Okay. All right. The other thing about Bethe realization is that it takes all of these, so I mentioned these analogs, these motivic analogs of classical spectra, and under Bethe realization, all of these motivic analogs go to their classical counterparts. So the motivic Eilenberg-MacLane spectrum goes to the Eilenberg-MacLane spectrum, KGL goes to complex K-theory, and Hermitian K-theory goes to real K-theory, and so on. Okay. Another thing, so the Bethe realization functor is a strong symmetric monoidal functor. So that just means it takes smash products to smash products. So this formula from this slide is going to give me a sort of analogous formula relating the homology and the mod 2 homology on the motivic side with the mod 2 homology on the classical side. And this is also, by the way, this is an isomorphism of comodules, if you like. I mean, in particular, there's this sort of relationship between the motivic dual Sternroth algebra and the classical one. So you expect, because of this here, you expect there to be some relationship between the motivic generators and the classical generators. So I just want to mention what that is. So in the motivic setting, this tau I you should think of as like the classical zeta I plus 1. And the motivic zeta I you should think of as the classical zeta I squared. This is useful because, so very often if you maybe know some sort of classical, description of some, like say homology group or some comodule or whatever, you can usually use this correspondence to guess the right answer motivically. Okay, anyway, moving on. So all of this, so there's all this structure here. And, one of the things is that you can also, like given a motivic rank spectrum E, you can just write down a E-based atom spectral sequence in exactly the same way I did in classical spectra. And you're also going to get that you have this nice homological description of the E2 term under the same sort of hypothesis. And again, namely that E star E is flat over E star. So there are two sort of notable examples that people have really studied a lot in the motivic side, and that's when E is the motivic Eilenberg-MacLane spectrum, and so this gives you what's called the motivic atom spectral sequence. And then the other example that people have also looked a lot at is the case when E is algebraic cobordism, which is this motivic analog of complex cobordism. And in that situation, you get what's called the motivic Adams-Novikov spectral sequence. So both of these have been studied a lot by Duggar Isaacson, and then also by, Isaacson, Wang, and Xu. And then the Adams-Novikov spectral sequence has also been studied by Levine. A lot of people have put a lot of effort into studying these two spectral sequences.
Hey, this is Dan. I think we should mention Hu, Cretan, Ormsby for
right,
the
yes,
Adams-Novikov.
Yes, I almost forgot them. Thank you. Thank you for reminding me. Yeah, the Hu, Cretan, Ormsby studied, also studied the Adams-Novikov spectral sequence. Thanks. Okay. Oh, yeah. So, all right. So, right. So here's something I want to highlight that will be very important for this talk. So there is a very interesting difference between motivic stable stems and classical stable stems. So there is this element called eta in pi11 of the motivic sphere. And it's called eta partially because when you take the Betty realization, it actually realizes to the usual element eta in pi1 of the classical sphere. But so now in the classical sphere, in the classical stable stems, eta to the 4 is 0. It's a nilpotent element. But here, motivically, eta is not nilpotent. All right. In fact, so eta to the j is not 0 for any j. But what you do have is that tau eta 4 is 0. So eta to the 4, while not being 0, it is tau torsion. And so that's why it goes away when you Betty realize. But because eta is not nilpotent on the motivic sphere, you can do the same sort of thing that I did earlier, and you can form the mapping telescope. So if you like, you have this eta inverted sphere, and this is just the co-limit. And you take S, and you multiply it by eta, and you keep multiplying it by eta over and over. And you take the co-limit of that. That's what this eta local sphere is. Now, the homotopy groups of the eta local sphere are just the same thing as inverting eta on the homotopy groups of the sphere. So when you look at these homotopy groups, you're just keeping track of the elements in the stable homotopy groups of the sphere, which are eta torsion free, right? And so you can ask what that is, and that was calculated by Andrews and Miller, and it was shown to be this very nice algebra here. So let's see. All right, so great. So here's a picture. So I took this picture from some Adams charts that you can find on Dan Isaacson's website. So this is the E infinity term of the motivic atom spectral sequence. So okay, so let me zoom in here. Let's see. So this thing here, this is mu9, and let me make this smaller. So and then this thing here, that's this thing epsilon. Okay, so you'll see, so here a red dot denotes, so here this is, here this is eta, so then this is eta squared, this is eta cubed, and this is eta to the 4. So this red dot is representing the fact that eta to the 4 is tau torsion. Okay, and so you see that there's a bunch of these elements, like for example, eta and mu9, which have these infinite eta towers showing up. So these red arrows indicate infinite eta towers. Okay, now the other thing I want to point out, so classically, classically, there's also an important region in the E infinity term of the atom spectral sequence, namely this one over here. So you'll notice that there's this region, and then there's a bunch of zeros, and then there's a bunch of stuff sort of over on this side over here. But this stuff in this region is related to the image of J. It's related to the V1 periodic part of the stable homotopy groups of spheres. And you'll notice that both epsilon and mu9 are in this region. So classically speaking, epsilon and mu9 are both in the image of J. And you'll also notice that all of these things in this region that I sort of highlighted, a lot of the elements, I guess around like 2/3 of the elements, have these infinite eta towers coming off of them. Okay, so this is something that will sort of come up later in the talk. But basically, let me just say it, end with this. So these, basically what I'm trying to say is that the eta local sphere also is inside this V1 periodic region from this calculation. That's the main point I wanted to make. Okay. All right, so now I think I can start saying some things about the actual work I did with JD. So let me start sort of sketching out some of the technical details related to studying this spectral sequence. Okay, so first off, so I told you that there was a thing called Hermitian K-theory. I didn't tell you what it was, but in the title of the talk, there's this little KQ, right? Now, if you were to take these analogies, so KQ is supposed to be the analogous thing for periodic real K-theory, and so Mahowald studied the atom spectral sequence based on connective real K-theory. So the first question is, what's the connective version for periodic Hermitian K-theory? And that's a bit complicated in the motivic category. So I'm not going to tell you what all that is, but I'm just going to tell you that it's this thing called the very effective cover of the Hermitian K-theory spectrum. And I claim that this is the correct definition, which I'll elaborate a little bit more later. But nevertheless, this is a thing you can define, and it's going to turn out that the little KQ is also a ring spectrum. It's a motivic ring spectrum, so you can also just look at the keq-based atom spectral sequence. And in this case, this is just what you get. This is what the spectral sequence looks like. This is what the E1 term is, and this is what the abutment is. Again, as classically, there's just no homological description of the E2 term. So you have to actually try and figure out how you're going to describe these groups. Okay. So what I would like to try and do, or what JD and I were motivated to do, was to say something about V1 and eta periodicity. So Mahowald said a lot about V1 periodicity using the keq-based atom spectral sequence. And part of the reason he was able to, that was a reasonable thing to do, was because V1, so as I said, V1 is the bot element. And so V1 is actually inside the homotopy groups of real K-theory. So it makes sense to use that spectrum to try and study V1 periodicity. But another key feature of real K-theory is that it also sees eta, right? And something that's also going to be true of this little KQ is that it's going to see eta. So it makes sense to also use this thing to study eta periodicity. So I want us to try and say some things about those. Okay, so roughly speaking, these are the three main steps in our analysis. So the first is that you have to actually try and describe the E1 page. And then the other thing is that you're going to use Betty realization to relate the KQ-based atom spectral sequence to Mahowald's KO-based atom spectral sequence. And you're going to try and use this comparison to lift differentials. And then the third step is you have to try and establish some sort of vanishing lines. And I'll elaborate on that later. Okay, so the first step is you need to calculate what these groups are for every S. So let's kind of just start with some low S's. So it seems reasonable to start when S is 0. So in that case, you can just sort of ignore this piece, this KQ bar, and now you're just trying to understand what the homotopy groups of KQ are. So as I said, KQ is this thing called the very effective cover. And I made the assertion that this was the correct definition. And the only reason I'm making that assertion is because its homology looks correct. So, by way of comparison, oops, let me make this thicker. By way of comparison, if you look at the mod 2 homology of real K-theory, that's A mod mod A1 dual, which is the subalgebra of the dual Steiner algebra. Let me write it more like this. So, which is a polynomial algebra on zeta 1 to the 4, zeta 2 squared, zeta 3, and so on. Okay, so if you use that correspondence I mentioned earlier, you'll see that this group really does coincide with that group under Betty realization. Okay, so this equality here was first, I guess, over C, that was first shown by Isaacson Shkemby, but this is actually also true over more general bases, and that was proven more recently by Anievsky, Rondiggs, and Ostfair. Okay, so because of this, this is why we took the very effective cover of Hermitian K-theory in the first place. Okay, so then because you know the homology of this thing, you can plug it into the motivic atom spectral sequence, and then you can use a change of rings theorem to give me a nice description of the E2 term, and so you get a very nice description of the motivic atom spectral sequence for this very effective cover of KQ. So let me show you a picture of what the E2 term looks like. So this is a picture of the E2 term. So a black dot just denotes an M2, which remember is F2 adjoint tau. And then a red dot denotes an M2 mod tau. So that's just a fancy way of saying an F2, but I'm trying to emphasize that on a red dot, if you give me the generator of a red dot, then tau on that generator is 0. Okay, so here, what's going on? So this dot here, that's eta squared, and that's eta cubed, and so on and so forth. So this tower is an eta tower. Now, if you ignored the red dots for a moment, then you would actually be recovering the usual Adams E2 term for a KO, right? So you get this Z, this Z2, Z2, 0, Z, 0, 0, 0, Z, right? So you recover the song. All right. So anyway, so this is what the Adams E2 term for KQ looks like. Now, a priori from this, it looks like maybe there could be some Adams differentials, but Adams differentials actually preserve the motivic weight, and so for degree reasons, there actually can't be any Adams differentials. So this is also the E infinity term. And so here's a picture of, so what I want to do is I'm going to sort of build up a picture of the E1 term of the KQ-based atom spectral sequence in a range. So at this point, we've figured out what the 0 line is. So here a black box is a Z adjoint tau, and then a black dot is again an F2 adjoint tau, and a red dot is just an F2. So you see this black dot is saying degree 0, 0 because you had this H0 tower in degree 0. And then you see this first eta here, and then the second eta, and then you get this you get this like tower of red lines, and so on and so forth. All right. So this is how you get the 0 line, and that's all there is to the 0 line. All right. So let's move on to the 1 line. So for the 1 line, you have to figure out what the homotopy groups of this thing are. So you have to figure out what the homotopy groups of KQ smash KQ bar are. So there's an atom spectral sequence for that, and this is what it looks like. So what's A mod mod A1 bar? So let me just tell you that it is, so KQ is a ring spectrum. So there's a map from the sphere into it. And if I apply homology to that, that gives me a map from M2 into A mod mod A10. And so then the co-kernel of that is A mod mod A1 bar. And this is a short exact sequence. Okay, so this is what you get. So basically, I mean, when there's a bar showing up, I mean, that just means you're getting rid of all of the elements in degree 0. Okay. All right, so how do you compute this thing? Well, it's complicated. So classically, there's a couple things that go on. So classically, Mahowald showed that there's a splitting into subcomodules. So these are subcomodules on the right, and these are finite subcomodules. And then, and these things he was actually just able to, he was actually able to give some very clever arguments that actually gave a very nice description of these things in terms of something called Adams covers, which I don't really have time to explain, I guess. Okay, but let me just say, so, but these things, these pieces, oh, oops, there's a typo here. This should be sigma 4j hz j. These things are actually realizable by certain spectra called the integral Brown-Gittler spectra. And so because you have this algebraic splitting and the pieces of the splitting are realizable by spectra, you might think that there is a topological splitting. And that's true. And that is in fact true. That's something that he proved. Unfortunately, at the moment, we don't know how to construct these Brown-Gittler spectra motivically. So we don't have the topological splitting. But we do have the motivic splitting. We do have the algebraic splitting. And the way you sort of accomplish that is you put on this notion of, you put on something called Mohold weight on the dual Stirnode algebra. You define what that means on the generators, and then you extend to all monomials by declaring that the weight of a product is just the sum of the weights. Okay, so when you have this notion of weight, then you can look at the subcomodules of A mod mod A1 dual spanned by the monomials of weight exactly 4k. So the reason for the 4k though is if you just look at the generators of this thing, you'll just see that the weights of the generators are always divisible by 4. So that's why there's a 4 showing up. In any case, it's a fairly straightforward exercise to just check that you do get this splitting of A1 comodules. So that reduces the problem to just calculating the X groups of these things. And I mean, that's also very complicated. I mean, so if you're familiar with this story, then you know that Mohold was able to show that the X groups of these things are Adams covers, but that's not exactly what happens motivically. Something a little bit more confusing happens. But what is true is that you can write down these short exact sequences. And so what this gives you is a way of inductively calculating the X groups of these HZIs. Okay, so the stuff here on the right-hand side, I haven't explained what that is, but I'll just say that it's not hard to compute those things. It's easy to compute those things. Okay, so I don't want to go through how exactly you go through this whole inductive process, but let me just say, let me just give you, here's some pictures. Oops, also there's a typo here. So this is sigma 4 HZ1 over here, and then this is sigma 4 2, sigma 8 4 HZ2. So here are just some pictures. So the way I figured these out was I just enumerated all of the monomials of weight 4, which, you know, because it's small weight, that's not so hard. And then here, a straight line, so a straight line denotes a square 1, and a curved line like this denotes a square 2. So in this case, this HC1 just looks like an upside down question mark module. Okay, so this is something that you can actually compute sort of by hand, but you can compute the X groups over A1 of this thing by hand. There's some pictures I'm about to show, and this is the E1 term of the algebraic Atiyah-Hirzberg spectral sequence for this upside down question mark module. So let me not go through all the details. I mean, for those of you that know those, so here a box like this, so a open box just denotes an M2 adjoined H0. So it's actually, so this box is just representing a whole H0 tower, but I suppressed that because I wanted to make it less cluttered. So this is a D1 differential that's showing up, and this D1 differential is just coming from the fact that the generator in degree 3 is connected to the generator in degree 2 by a square 1. And then because the generator in degree 2 is connected to the generator in degree 0, you have a D2 differential like this. And so then you can get to the E3 page, and then it just collapses. And then there's some hidden extensions that you have to resolve. Okay, but nevertheless, this is a picture of X over A1 star star of HZ1. Okay, so now I can put this into this picture of the E1 page of the keq-based atom spectral sequence. So this first black box that's coming from this over here, and then the second black box, that's coming from this over here, and then you get this eta tower over here, and then you get another black box. This extra black box over here that's coming from a sigma 8 for HZ2, which I haven't told you how to calculate, but I mean it's the only contribution of HZ2 in this range, so I'm kind of ignoring that for the most part. But in any case, so now let's move on to the 2 line. This is what you get. So from that decomposition I mentioned earlier, you can split the calculation into just calculating these X groups of these kinds of things. So let me not tell you exactly how you compute this. I mean, you compute the X groups of this thing again by an algebraic Atiyah-Hirzebruch spectral sequence. But this is the answer. This is what you get. And I want to point out something here. So for the people who know this sort of stuff in the Zoom, so classically, what you expect. So HZ1 is supposed to give you HZ1 tensor HZ1 is supposed to give you a 2 cover of BO. So the idea of this is that you're supposed to have a pattern of BO like this, and then you took the atoms cover, so you just took the 2 line and you looked at everything above the 2 line. All right, and if this was really actually just a BO, this would make sense because I'd be ignoring the red dots, right? But if I were working motivically, and I took the 2 atoms cover of KQ, then you would expect there to be a whole infinite eta tower on this little dot in degree 2, 0, but there isn't one there. So that's why the motivic calculation is a little bit more involved and a little bit more complicated, because you don't have this nice description in terms of atoms covers. Okay, but nevertheless, you can write down you can figure out what the 2 line is, and then there's also this 3 line, this thing of the 3 line. This part is coming from sigma 12. 6 of HZ1 tensor itself 3 times. Okay, so this is what the E1 term of the keq-based atom spectral sequence looks like in the range up through 10. So there's no contributions from the higher lines in this range. Okay, so now at this point, I need to say some words about how you maybe get differentials. So again, the way you do this is you use Betty realization. So Betty realization is a strong symmetric monoidal functor. So what that implies is that you actually get a morphism of atom spectral sequences. So there's a morphism from the keq-based atom spectral sequence to the ko-based atom spectral sequence of the Betty realization. So you can use this to deduce a lot of differentials, and this has been used in other situations as well, like in the motivic atom spectral sequence and what have you. But anyway, the main thing here is, this is kind of a hard statement to explain, but this is a classical result of Mohoald. So let me just tell you what this sort of means practically. So let me say, so the second part, that's more related to some sort of image of J stuff. So this is more related to something like if you're familiar with the calculation of the K1 local sphere or something, this is more what the second part is about, is how you're getting the torsion in the K1 local sphere or something. But the first part, that's more like saying, so the first part is sometimes called bounded torsion. And the reason for that is because of the following. So if you give me an element of the E infinity page of the KO-based atom spectral sequence, and it's in the 2 line or above, then it can at most be a 4 torsion class. It can't be an 8 torsion class. It can't be a 16 torsion class. It's a 4 torsion class at best. And then there's other things that this first part tells you. It tells you things that like V1 squared on anything in the 2 line or above is 0 necessarily. V1 times something in the 2 line or above could be non-zero, but V1 squared times it is necessarily 0. So it implies things like that. And so there's a similar sort of thing that happens motivically. This is very complicated, and I don't want to go through the argument, but again, these two latter parts are somehow related to an image of J thing. But this first part is some sort of motivic version of this bounded torsion theorem. So it again implies things that, like in the two line and above on the E infinity page, you are for torsion. It also implies things that, like eta squared, if you give me an element x of the two line or above, then eta squared times x is necessarily 0. That's what this first part really means. Okay, oops. So that's just,
yeah.
okay.
I was just going to let you know that it's about time to wrap it up. So.
All right, so I'm almost done. So yeah, so let me just say this is, so you can calculate the 0 and the 1 line of the keq-based atom spectral sequence. And this is what it is. And so the thing I want to point out is that you see a lot of these eta torsion free things in the 0 line and in the 1 line. Okay, so this y, by the way, this is the thing that detects epsilon. Okay, so let's see. Let me end with, so there's some pictures here I can show people who are interested later, but I just want to end with one thing that I think is very interesting about the spectral sequence. So there is a naive 1/3 vanishing line that's very easy to prove. So what I mean by a vanishing line of slope 1/3 is that so there's a line of slope 1/3 through the origin on the E1 page of the keq-based atom spectral sequence, so that if you're above that line, you're just in 0 groups. All of the groups above that line are 0. So that has a very interesting consequence. It tells us that all of the eta periodic elements in the sphere, at least over C, are detected in the 0 and the 1 line of the keq-based atom spectral sequence. And so here's like a picture sort of illustrating this fact. So the question is, how could you have missed an eta torsion-free element? Well, you could have had a sequence of elements in the higher lines of the spectral sequence, but which were connected to each other via an infinite sequence of hidden extensions. But if you look at how such a family grows, it grows along a line of slope 1/2. But we have this this naive vanishing line of slope 1/3. And so that means that, you know, whenever you have a line of slope 1/2, that's eventually going to overtake a line of slope 1/3. So such a possible counterexample necessarily always finds itself in the 0 region. And so there's no sort of eta torsion-free element in stable homotopy groups of spheres that we've missed. So they're all on the 0 and the 1 line, and you can use this to recover the Andrews-Miller results. So anyway, so blah blah blah, future work. Thanks for your time and attention.
Okay,